Thank you.
All right, thank you. All right, so today I will be talking about the relationship between trigonometry and complex numbers. And we'll be going over the polar form of complex numbers, the exponential form of complex numbers, uh, the roots of unity, and then some problems. All right, so first we'll be talking about the polar form of complex numbers. Okay, so on Monday, we talked about complex numbers and we expressed them in the form of a plus bi, uh, and this can also be denoted as a comma b, since it's like a coordinate system. And these are called rectangular coordinates, or the rectangular form of complex numbers. However, we can also describe these using something called polar form, which is using a distance r and an angle theta. So here we have a complex number z, and here we have the distance r, and then the angle theta. So it's like this. And then basically, the coordinate r comma theta corresponds to r times cosine theta plus I sine theta. So cosine theta here, then I sine theta. And then keep in mind that this I is the same one as the one we talked about the other day, square root -1. And then we also need to convert rectangular coordinates into polar coordinates. So here we have how we do it. So r is equal to the square root of a squared plus b squared. And this is also equal to the magnitude of z. Since, yeah, you can see the definition is the same. Uh, and we also have that theta is equal to the arctangent of b over a. Okay, so I'll just help visualize. So say we have some z like here, and then this z is equal to a plus bi. So then we can draw it like this, and then in the real dimension there's a, and then on the imaginary dimension there's b. So we can see why this is true. We have the radius or r, which is the distance, this here, right? And then we can find this just using the Pythagorean theorem, right? A squared plus b squared equals r squared, and take the root. And then theta is here. I'm going to try to find theta. So we can just apply trigonometry. We know that tan of theta equals to b over a. So then arctan of b over a is equal to theta. However, notice that this is not always true, and it will come up in the next slide. And sometimes we'll also need to find the rectangular form from the polar form. So yeah, going back to this, we have theta, then we have r. Then we can just apply like the sine and cosine. Then a is equal to r cos theta here, and b is equal to r sine theta. We can see why this is true, since we have like this is a, this is b. If we use cosine, we have cosine theta is equal to uh, a over r or something like that. And then yeah, we can just do some manipulation and then get this. Okay, so yeah, here's some examples of converting from rectangular to full polar form and vice versa. And then now I'll talk about how I need to evaluate the arctangent. Since for our polar coordinates, they can be like anywhere, like here, they can be in any of the quadrants, right? However, arctangent will only give angles that are within the quadrant 1 and quadrant 4, like these two quadrants, since that's just how arctangent is defined. So that means if we have some coordinate like this coordinate here, if we try to plug it in to our arctangent, the angle theta should be like this. However, arctangent will actually give a result like this, which is like exactly 180 degrees off. So we counteract this. So for quadrant 1, that's within the domain of arctangent. So theta is just equal to arctangent of b over a. And then for quadrant two, this is outside of the range of arctangent. So we have to counteract this by adding a pi to the arctangent, which is just 180 degrees. Uh, and then same thing for the third quadrant. It's also outside of the domain of arctangent. So we have to do the thing with the pi again. And then for quadrant four, it is within the range of the arctangent, so we don't have to do anything. And then yeah, also note in these examples, I'm always using radians instead of degrees. Okay, now we can discuss multiplying and dividing in polar form. So as you can see, it's very easy. You just multiply the two distances together, right? And then you add the two arguments, which is like the angle together. And then we can see why this is true. If we have, say, R1 uh, cosine theta 1 plus I sine theta 1. And then we want to multiply this by R2 cosine theta 2 plus I sine theta 2. So these will be like two complex numbers. We can see that this is equal to R1, R2. So that's this part here. And then multiplied. And then we can expand and multiply the remaining part. So we have cosine theta 1, cosine theta 2, and then plus I sine theta 2 cosine theta 1. Also, apologies for my bad handwriting. And then I sine theta 1, uh, cosine theta 2. And then we have two i's, so it's minus sine theta 1, sine theta 2. Okay, so now we can notice that for the real parts, we have cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. And this is the same as the sum of cosines identity. So then this part is equal to cosine of theta 1 plus theta 2. And then for these parts, they both have a factor of I. So if we move the factor of I, we see that it's the same as the sum of sines formula. So then this part is equal to I sine of theta 1 plus theta 2. And then yeah, we can see this is the exact same as our formula here. And then for division, it's very similar. You just replace z of 2 with like 1 over 0, 2, and then the same thing applies. And here we have an example. You can see uh, we multiplied the two like uh, distances. The 2 times 3 is 6. And then here, the first complex number, the argument is pi. The second one is pi over 2. So we just add these and we have 3 pi over 2 here. So yeah, it's pretty simple. Now, with this multiplication rule, we can arrive at De Moivre's theorem, which is as stated here. And you just basically apply what we did multiple times to arrive at the exponentiation. And this works for all real n. And yeah, so here we have an example, 1 plus I to the eighth. If we try to compute this by hand, it'd be like really painful. However, we can use De Moivre's theorem and it becomes much simpler. We have 1 plus I to the eighth is equal to this in its polar form, root 2 cosine pi over 4 plus I sine pi over 4. Uh, and then using De Moivre's theorem, taking that to the eighth is the same as taking root 2 to the 8 times cosine 2 pi plus I sine 2 pi. Since you multiply all these by 8, and we get 2 pi. And then this is equal to 1, and this is equal to 0. So then this entire thing is equal to 16. So yeah, De Moivre's theorem is very important. Okay, here are some example problems. I'll give you guys about 5 minutes to work on these, and then if you have an answer, you can send it to me in chat. All right, it's now been about 5 minutes, so I'll go over the solutions to these. So here we have z equals 3 cosine 20 degrees plus I sine 20 degrees, and w is 5 cosine 100 degrees plus I sine 100 degrees. So to find z times w, we can just directly apply the multiplication polar for polar form of complex numbers. So we first multiply the distances, so 3 times 5 is 15. And then we can add together the angles. So here we have 20 degrees, and here we have 100 degrees. So our new angle will be 120 degrees. So thus the answer will be 15 times cosine 120 degrees plus I sine 120 degrees. And then for the second one, we have to first find the reciprocal of W. So that will be the same as finding the reciprocals of the real part and the imaginary part here. So the reciprocal of 5 is 1/5, and then the reciprocal of this complex number uh, is is the same as negating its angle, since we learned yesterday that, or not yesterday, on Monday, that like, we have some complex number, then 1 over that complex number is just flipping it over the x-axis. So like this. So this will be cosine negative 100 degrees uh, plus I sine negative 100 degrees. So then we can just multiply this and this, and then we get 3/5 of cosine negative 80 degrees plus I sine negative 80 degrees. And then if you guys want, you can also clean this up so there are no negative arguments in here. And then for the second question, we can directly apply De Moivre's theorem. So we first take 2 to the third, so that's 8. And then we multiply each of the angles by 3. So then 20 degrees becomes 60 degrees. So then this becomes 8 times cosine 60 degrees plus I sine 60 degrees. However, this problem is asking for the answer in standard form a plus bi. So we have to evaluate this. So cosine 60 degrees is equal to 1/2, and sine 60 degrees is √3 over 2. So we multiply this out, then this is equal to 4 plus 4i √3.
Yeah, 4 plus 4 root 3.
Yes. And then for the last one, we can apply De Moivre again. So √3 to the 6th is equal to 27. And then we multiply the angle by 6, and that's 5 pi over 3. So then the answer is 27 times cosine 5 pi over 3 plus I sine 5 pi over 3. Are there any questions? All right, I'll move on then. So now we'll do section 2, which is the exponential form of complex numbers. So here we have e to the I theta is equal to cosine theta plus I sine theta. And notice that this is like part of what we had before with the polar, except in the polar form, it was multiplied by r. So yeah, this is just a way for us to express this part of the polar uh, form of complex numbers. And yeah, e to the I theta is equal to this. And I won't get into how we arrive at this. It basically involves like something to with like Taylor series. And then the e here is this famous constant 2.71828 dot dot dot.
How did
Uh,
they figure that out?
what?
How did they figure that out then?
It's related to Taylor series and it's very complicated. Uh, so the complex exponential e to the I theta is a point on the unit circle at angle theta. And this you can see why this is true, since like this is the same as in polar form, and the distance is 1. So we can just like plot all the theta and it looks like a circle. Uh, and yeah, and there's a famous identity. It's e to the I pi plus 1 is equal to 0. And this is what you get if you replace theta with pi here, right? And then you evaluate it. And people really like this equation since e I pi 1 and 0 are all really important constants in mathematics. And this equation contains all of them. So yeah, it's really nice. And then any complex number can be written uh, using uh, the exponential form. So z equals r times e to the I theta, where r is equal to the magnitude of z, and theta is the argument of z. And yeah, the argument is basically just the angle. And you can see this is very similar to what we have to the polar form, since this is still an r. It's just the e to I theta is replacing the cosine theta plus I sine theta. And then we can use all three of these forms. So rectangular form is very good for addition and subtraction. Since when you add and subtract, you can just like add and subtract the real
I think
and
exponential is also good for multiplication and division.
oh yes, it is. But it's
Yeah,
also good for powers and roots too.
yeah, like the polar form, it's kind of messy.
Yeah, since if you try to take the power and root of some of the stuff in polar form, well, I guess you can use De Moivre's, but it's not as easy.
Yeah, basically you have to use like
Yeah,
and angle identities.
yeah. So yeah,
And
basically,
that's basically just Chebyshev polynomials.
yeah, we won't talk about Chebyshev polynomial today though. It's like a bit beyond the scope. So yeah, and here you can see an example of a complex number in all three of these forms on the bottom. And then here, how you do the operations in exponential form. So to multiply two, you just multiply like the magnitudes. Then you add the arguments. So like basically the same as in polar form. And then same in division. And then for exponentiation, you exponentiate both the magnitude here and also the next part. And since there's already an exponent in the e to the I theta term, it's really easy. You just multiply I theta by n. And then conjugation, you just negate the I theta since that negates the angle. Okay, and then here's some examples. I'll give you guys like let's say 10 minutes and then message me if you have anything. For some reason, I can't look at the chat without it like pausing the presentation. So maybe you guys should message Catherine instead. Wait, can you guys still see my screen when it's paused?
Yeah, we can see your screen right now.
All right. Oh, that's good. Oh, it's been about 10 minutes, so I'll go through the answers now. So find 6 to the I pi divided by 3 in rectangular form. We need to first find e to the I pi over 3. And as established earlier, this is equal to cosine pi over 3 plus I sine pi over 3. And then we can evaluate this. This is equal to 1/2 plus I root 3 over 2. So we just need to multiply this by 6. And then we get 3 plus 3I root 3. Yeah. Now for the second one, we have -3 plus I root 3 to n. This needs to be a real number. So we can express this in exponential form. So if we look here, this number is in the second quadrant. So arctan won't give us the right answer. So we can first try using arctan here. This will be root 3 over -3. And arctangent of this will be equal to arctangents of this is equal to I think negative pi over 3 or something. Uh, and then uh, we can wait, uh, and then we need to evaluate when this is real. So we know that this is real when this is equal to pi or 2 pi or some multiple of pi, right? So then uh, this will be real whenever uh, n is a multiple of 3, yeah. Oh yeah, and then since arctan is wrong, we have to add a pi here, so this is 2 pi over 3. So yeah, we can see that this is a multiple of pi whenever uh, n is a product of 3, or a multiple of 3. Uh, and then for this one, we need to evaluate -2 root 3 plus 6i to the 8th. And then if we expand this, it will take forever since there's an 8th power. However, we can use the rules we learned. So this is equal to, if we express this, this is equal to, I believe, 4 root 3 times uh, times cosine of, I think, the cosine of 2 pi over 3 plus I sine 2 pi over 3, and then this to the 8th, and this to the 8th. And then uh, this part is equal to 4 to the 8th times 81. Then I don't expect you to evaluate that. And then this part on the right is equal to cosine of 16 pi over 3 plus I sine 16 pi over 3. And then, yeah, this is equal to cosine of of 4 pi over 3 plus I sine 4 pi over 3. And then, yeah, this will just be the product of that, of these two. Okay, and then lastly, we need to express negative 32i in exponential form. So first is the negative 32. Then we just need to find I in exponential form. And then I is over here. So we can see that this angle is pi over 2. So this will be e to the I pi over 2 here. Oh wait, shoot, there's a negative here. So it's actually negative I. So it'll be 3i pi over 2. Sorry. Yeah. Alright, now we'll be talking about the roots of unity. So what are roots of unity? Well, an nth root of unity is a complex number z such that z to the nth is equal to 1. So yeah, basically, they're just complex numbers that satisfy this equation. And then we can try finding them for arbitrary n. So we're gonna see here that 1 is equal to e to the I times 0, and it's also equal to e to the I times 2 pi k for k in the integers. And yeah, this is just e to 0, which is 1. And then this, we can use what we learned about the exponential form. So 2 pi is just like a full circle. So when we multiply by some multiple of 2 pi, it's like some multiple of going around the circle. So this is just 1 because it arrive at the same point. And then from here we can manipulate it. So z to the n is equal to 1, since that's like the equation we're starting out with. And then this is also equal to e to the I n theta, since, yeah, uh, since e to I theta is equal to z. And then this becomes e to the I n theta is equal to e to the I times 2 pi k, since that's another way we express 1, right? Like this. And then we can set these two things to be equal to each other by taking the natural log of both sides. So then we have I n theta is equal to I times 2 pi k. And then we can divide both sides by I. And then we have n theta equals to 2 pi k. And then we divide both sides by n. And then theta equals to 2 pi k over n. And then, so omega k, which is what we use to denote a root of unity, is then equal to e to the 2 pi I k over n for k equals 0, 1, 2, dot, 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 n minus 1. Notice that these, well, for the first one we did k in the integers, and for this one we did 0, 1, 2, dot, 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 n minus 1. They give the same result since after n minus 1, like for n plus 1, etc., these will just like map back onto like some stuff we already have. So they're the same, and so we don't really need to count them. So then the kth nth root of unity will be yeah, this e to the 2 pi I k over n, and then it's also equal to cosine 2 pi k over n plus, oops, there's supposed to be an I here, I sine 2 pi k over n. And then these are endpoints that are equally spaced on the unit circle, as you can see here. And these are spaced by 2 pi n radians apart each time. So yeah, here we have an example for the fifth roots of unity. Okay, so in this example, we have to find the cube roots of unity for n equals 3. So those will just be the solutions of z cubed equals to 1. And then we can just directly apply what we learned. And then we have that's the third roots of unity are e to the I pi I k over 3 for k equals 0, 1, 2. And then it directly yields these. Yeah. So you can just use this to find roots of unity for a lot of things. Okay, so now we need to talk about primitive roots of unity. So an nth root of unity z is called a primitive nth root of unity if z to the n is equal to 1 and z to the k is not equal to 1 for k equals 1 to dot 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 n minus 1. For example, I is the primitive fourth root of unity since no I to the k equals to 1 for k equals 1, 2, 3. However, I is not a primitive root of primitive eighth root of unity since I to the fourth is equal to 1 and 4 is less than 8. So like in other words, if you take like a primitive root of unity like z and then like you let k equal to like 0, 1, 2, dot 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 n minus 1, then z to the k will generate all of those terms, all of the nth roots of unity. And we see why this is not true for like non-primitive roots of unity since like these loop early. So like for example, I for in terms of the eighth roots of unity, it only generates 4 of the eighth roots of unity. Uh, and not all of the eights. And it's very easy to find primitive roots of unity. Let omega equal to e to the 2 pi ki over n. And then omega is a primitive nth root of unity if and only if the greatest common divisor of k and n is equal to 1. And you can see why this is true. Like if you multiply k by like 1, then k by like 2, then k by like 3, dot dot dot. And then we like take these all mod n. And this will be like k, and then this will be like some other thing, etc. But since the greatest common divisor of these is equal to 1, that means these do not loop all the way until we get to k equals to k times m plus 1. And then only from here, this is congruent to k again. So yeah, this is why that is true. And then there are a lot of properties of the roots of unity that are very important to us. And as established earlier, all the nth roots lie on the unit circle. So the magnitude of omega is equal to 1. And then it's also like intuitive because like z to n is equal to 1. So like it makes sense that this part's magnitude is 1 because otherwise like the magnitude of the big thing will be a lot more than 1 or less than 1. And these are also all equally spaced by the angle 2 pi over n. And yeah, we saw a demonstration of that earlier with the circle. And it's also like a fact of how it's formed. It's like 2 pi is like a full circle, and then we just add more full circles, and then divide by n because nth root unity. Uh, and the sum of all the nth roots is equal to 0. So this one's a little harder to see, but so going back to our original equation, we have z to the n is equal to 1. So we can rearrange this into z to the n minus 1 is equal to 0, and it's just a regular polynomial. And then from here, we can use Vieta's formulas to find the sum of the nth roots. And the second term is equal to 0. So we have 0 over 1, and that's just 0. So that's why the sum of all the nth roots of unity is 0. And then for the product of the nth roots of unity, we can just use Vieta's formula again. So we have -1. So then we have -1 over 1. However, sometimes this will be positive, sometimes this will be negative. And this determines on the degree of the polynomial. So that's why we have -1 to the n plus 1 here. And then if omega is a primitive nth root, then all the roots of the nth roots of unity will be omega squared dot 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 omega to the n minus 1. And this is what I said earlier about taking powers of the primitive root to generate all of the nth roots. And then lastly, we have that the conjugate of the kth root of unity is like same as the n minus k. And yeah, you can see why if we have a unit circle. Then it's like this, right? All right, so here's some example problems. I'll give you guys about 10 minutes and then message me if you have anything. All right, it's been about 10 minutes, so I'll go through these. All right, so solution of x to the eighth equals to 1. So these are just the eighth roots of unity. So then this will just be e to the I pi over 4, e to the I pi over 2, dot dot dot, all the way to e to the 7 pi, I 7 pi over 4. And then you can evaluate these if you want, but it's plus 1, plus minus 1, plus minus I, and then plus minus root 2 over 2, and then plus minus I root 2 over 2. So yeah, that's x to the eighth equals to 1. And then for the primitive 12th roots of unity, we can see which numbers are relatively prime to 12. You see that there's 1, 5, 7, 12. So then the primitive 12th root of unity will be e to the pi over 6, I pi over 6, e to the 5 I pi over 6, e to the 7 I pi over 6, and then e to the 11 I pi over 6. And then this is equal to root, no, yeah, oh yes, root 3 over 2 plus I root I over 2, and then negative root, and it's just plus minus these, yeah, plus minus these. And then for the last question, we have omega equal to e to the 4i over 7, and then we need to evaluate this long expression. So since omega is equal to e to the 4i pi over 7th, it's one of the 7th roots of unity. So omega is a solution of z to the 7th equals to 1. And then we can rearrange this into z to the 7th minus 1 equals 0. And then notice that this is factorable since z equals 1 is a factor. So we can divide this thing by z minus 1. And then we just factor it. And then it gives this polynomial. And then these two are equal. So we can see here that this is like very similar to this. And we know that this entire thing has roots of the 7th roots of unity. And then since 1 is one of the 7th roots of unity, this will have the 7th roots of unity except for 1. So it can also be factored in some way. And it can be factored like x minus like the first root of unity, and then x minus like the second root of unity, dot dot dot, x minus like on the 6th root of unity. So it can be factored like this. And notice how these two forms are like very similar. And then since omega is a primitive root of unity, that means it'll generate all the roots of unity. And then notice that if we plug in x equals -2 to this, then this becomes -1 to the 6th times 2 plus omega, and 2 plus omega squared, since it's a primitive root of unity, and then dot dot dot, and then 2 plus omega to the 6th, and that's like what we want. So that means all I have to do is plug in -2 into this polynomial. So yeah, we can do that. And then this will be 64 plus 32 plus 16 dot dot dot. Uh, Wait, sorry, I think these should be pluses. My bad. So then this is minus, then -8, then +4, -2, and then +1. And then this is equal to 32 plus 8 plus 2 plus 1, and that's 43. So yeah, the answer to this one is 43. And then here's another example we have. I'm not gonna give you guys time to do this. I'll just go straight to the answer. So GZ is this polynomial. And if we multiply both sides by z squared, then we get z to the 8th plus z to the 6th plus z to the 4th plus z squared is equal to z squared times gz. And then uh, notice that this is very similar to this. So that means that we can subtract gz on both sides. So then we get z squared minus 1 times gz is equal to z to the 8th minus 1. And then we divide both sides by gz squared minus 1. And then we have gz is equal to z to the 8th minus 1 over z squared minus 1. And then the roots of this are just like when this is equal to 0, excluding when this is equal to 0. So thus the roots of g are the 8th roots of unity excluding plus minus 1, and that's when z squared minus 1 is equal to 0. Okay, so now we have some more difficult problems. So I'll give you guys about 10 minutes to work on these. All right, it's been about 10 minutes. So I'll go over these solutions. All right, so for z cubed equals negative 4 root 2 plus 4 root 2i in exponential form. We first find this in exponential form. So first is like the magnitude, and the magnitude of this is it is 8. And then we find the these are the I theta part. So if we look on a graph, this is over here in the second quadrant. So if we find the arctangent of this, and then we add pi, we get 3 pi over 4. So that is what this part is equal to. Okay, and then now we have z cubed is equal to this. So if we get rid of this part, then it's the same as multiplying all of z by 2. Right, so this is just like 2. And then e to the 3i pi 4 over 4. If we take the cube root of that, then that's I pi 4. However, we must also include like the 2 other solutions. So then we also have to add in uh we have to add in this to account for the other solutions for k equals 0, 1, 2. So yeah, z will then be equal to 2 e to the I pi over 4 plus 2 pi k over 3 for k equals 0, 1, 2. Yeah. Okay, and then the next one, determine all the integer values of theta with 0 degrees less than theta degrees less than or equal to 90 degrees, for which this is a real number. So this is equal to e to the I theta, and this is multiplied by 75, it's 75 I theta. And then for a real number, we know that e to the I 180 degrees is equal to -1, and then e to the I 360 degrees is equal to 1. So basically, if this thing is divisible by 180, then it's a real number. So we have 75 I theta, and then let's just do k to iterate through all the theta. And then we have 180 degree I theta, and then for some multiple, so let's say m, and then these cancel. We have 75k equals to 180m, and then we can simplify some more. So then we see that k must be a multiple of 12 in order for this to be a real number. So then thus theta equals to 0 degrees, 12 degrees, 24 degrees, dot dot dot, all the way to 84 degrees. Yeah. Okay, and then this last one. Oops. We need to express sine of 5 theta in terms of sine theta. Okay, so to do this, we can see that cosine theta plus sine theta to the 5th, or I sine theta, is equal to cosine 5 theta, oops, cosine 5 theta, plus I sine 5 theta. And this is by De Moivre's theorem. So that means that I sine theta, or I sine 5 theta is equal to cosine theta plus I sine theta, the 5th minus cosine 5 theta. Alright, so now we just need to express all of this in terms of sine theta. So we expand this term here, cosine to 5th theta, and then plus 5 cosine theta, uh, and then sine theta, and then plus, no, minus cosine 10 cosine 3 theta, sine 2 squared theta, and then minus 10I cosine squared theta, sine cubed theta, and then plus 5 cosine theta, sine to the fourth theta, and then finally plus I sine to the fifth theta. Yeah. Okay, so now we can start. These are like the same, and then we have this. So we know that cosine squared theta is equal to 1 minus sine squared theta. So yeah, we can get replacing. We have, oh wait, missed a step. So since this is I sine 5 theta, that means only terms with an I in it will contribute to the final answer. So over here there's an I, over here there's an I, over here there's an I. And these two terms here do not include an I term, so they won't contribute to the I sine 5 theta, so we don't care about these. Okay, and then we can use this property here. So we have 5I 1 minus sine squared theta, and then all this squared sine theta for this term. And then for the next term we have minus 10I 1 minus sine squared theta multiplied by sine cubed theta. And then for this last term, there's no cosine in it, so it's already in the right form. And then all this is equal to I sine 5 theta. Okay, and since we're trying to find this, we're trying to find sine 5 theta and not I sine 5 theta, you just divide everything by I. Yeah. So then we're left with this, and then you can simplify this if you want. And then this yields 16 sine to the fifth theta, minus 20 sine cubed theta, and then plus 5 sine theta is equal to sine 5 theta. Yeah. So yeah, it's quite tedious, but yeah, you can do it eventually. Okay, and then here's some more problems. I'll give you guys 10 more minutes to work on these. It's been another 10 minutes, so I'll continue with these solutions. Okay, so for the first one, notice that x and y are both like reciprocals of each other, and these imaginary parts cancel out. Notice that n equals 1 is already a solution. And then if we plot these on like the grid, notice that these are also third roots of unity, right? So this one's x, this one's y. So then for successive powers of n, just like shift these around like this. And then notice that these only equal 1 when n is divisible by 3. And when they're not, then there's this -1/2 part on both of them. And then that's also -1. So that means that n can equal anything such that 3 doesn't divide n. So like, yeah, any n such that this is true, basically. Okay, for the second one, you could definitely do something similar to what we did earlier with the finding sine 5 theta with just the sine theta. But another way is also to use the tangent double angle formula. So it's like this. There's the tangent double angle formula. And then I won't go through all this, but you could basically just apply this like 3 times. And then you get that angle A theta is within the second quadrant. So yeah, that's this one. Okay. All right, now we have some challenge problems. Okay, I'm not gonna go through the solutions for these since they're very hard, but you can think about them on your own. Uh, so yeah, we'll just work on these for the remainder of class until the very end, and then I'll say what the homework is. So yeah. All right, so if you guys want to like learn more about these problems, you can like stay around after class, or you can ask during our office hours on Saturday, I believe. All right, so now your homework will be from the book Precalculus Enhanced with Graphing Utilities. And yeah, it's just these, yeah. And if you guys need help on the homework, you can come to our office hours on Saturday, uh, same time as class, I believe. So yeah, that's it for today.